Okay, folks, so we're going to take a look at problem number 104 here in your textbook. And in this problem, this collar here is rotating at 0.5 radian per second at the instant shown, and the rotation rate there is increasing at about 2 radian per second squared. So what we're going to be trying to calculate here is the normal forces acting on this object as it moves through this confined area here. So I'm going to take a moment here and pause this and think about what these force vectors are going to look like, and then I'll be back. Alright folks, so let's see, I've drawn the free body. I paused it so I could take the time here to draw these vectors here nice and straight. And one thing I want to point out is that we have two different normal forces now. We have a normal force between this surface and this ball, and then another normal force here between this surface and this ball or object or whatever it is. So these two forces are responsible for pushing this ball through this path here. Now, you'll notice I did not include a gravitational force. This object is 0.5 kilograms here. So these, that's going to give us about a 5 Newton force, which has a magnitude about 1 pound. These normal forces, in all likelihood, are going to be the dominant forces in the problem, so I'm not going to worry about a gravitational force. Now, the next step is to choose a set of coordinates to sum forces in. And it turns out, looking at this, that the radial coordinates, at the instant this is shown, are actually the same as the Cartesian coordinates. If you look at this, the r hat direction would be up, and then the theta hat direction would be this way. So it doesn't really matter what direction, whether we sum these in the r direction, if we call that the r direction, or the y direction. I guess I'm going to go ahead and call it the minus r hat direction. The plus r hat direction is outward here. The minus r hat would be inward. So I can write an equation here that basically says this. Sum of all forces in the, I'm going to put the minus r hat direction here, equals ma. And having said that, to tell you the truth, I think what I'm going to do is change this to the plus r hat direction and let the sign on the acceleration kind of fix itself. We're going to have to calculate the radial acceleration, based on these relationships here, that r is equal to a over theta. Here's my theta dot, here's my theta double dot. So not having a really good sense for whether or not the acceleration is going to be up or down, I think what I'll do here is just call outward positive as usual. So in the instant shown here, that would be this way. So looking at the free body and writing that equation, we're going to have n times the cosine of some angle here. Now in this picture, the angle that I've labeled or used is that one. We're going to go ahead and find that in a minute. This normal n2 does not have a component in the radial direction, so that's it. That n cosine theta, there's your net force in the radial direction. So that's going to equal m a sub r, and we'll go ahead and we'll find a sub r in a minute. Okay. Next step would be to sum all forces in the theta hat direction. In this example, this way would be the positive theta hat direction, and that's going to equal ma sub theta. So looking at the free body, there are two forces now that have components in the theta hat direction, n2 and n1 sine alpha. So I'm going to go ahead and add these. So we're going to have n2 plus n1 sine alpha equals ma sub theta. So here's the two Newton's second law equations for this free body. The next step will be to calculate those accelerations and then calculate the angle alpha. So I think what I'm going to do here is, so the video doesn't get too big, is just pause it, move some stuff around, and work through the calculations, and then I'll turn it back on. So, boop. Okay, folks, so I've done a little work here while this was paused. I wanted to take my time and draw these vectors as nicely as I could, and I tried to color code them. So, look at the original picture here. In red, these are the normal vectors, n1 and n2, just like before. In blue, I put the unit coordinates that we're working in, the theta hat direction, the r hat direction, keeping in mind outward is considered positive. This is a picture of this particle with a couple different things kind of superimposed here. So here's the particle. Here are the normal vectors, n1 and n2, again, both in red. Here are my blue unit vectors, theta hat, r hat direction. And now I'm going to start working on this angle here that we have to find. Now, Imagine now that this particle moves along this path, a small displacement ds. So I drew that vector in black. That's this one right here. There's my ds vector, small displacement. That's equivalent to, in black, an r d theta. Now that's coming from imagining theta changing a little bit. And then a minus dr. And again, I put the minus sign here because this vector points inward. So dr generally is considered outward positive. So this interior angle here, this is alpha. And the tangent of alpha would equal minus dr over r d theta. So simplifying this a little bit, tangent alpha can be written minus 1 over r dr d theta. And looking right here, r is equal to a over theta. So dr d theta would be minus a over theta squared. So tan alpha is going to end up being positive 1 over r times a over theta squared. And this is going to be some, this thing will be some positive number when I calculate it. That's going to give me a positive value for tan theta. And once I have alpha. Once I have alpha, I'll then know this angle and this angle right here. Now, then I can go and start writing my Newton's second law equations. So I'm going to pause this again here while I work out what alpha is, and then we'll talk about how to do the rest of this. Okay, folks, so I got this worked out. I put in the numerical values here. Basically what I did is I took tan alpha equals 1 over r. Now, r, looking over here, is a over theta, so 1 over r would be theta over a, and then that's times a over theta squared. So we end up with 1 over theta out of that. This is at 90 degrees, or in radians, pi over 2. So when I solve this, I get that alpha is... what do I get out of this? 32.5 degrees. So, I think what I'm going to do is stop this video right here. It's 7 or 8 minutes long. It's probably starting to push a gig. I'm going to stop it here, call this part 1, and then finish this problem under part 2. So, please stay tuned.